There we are. Okay, well, I guess you kind of got the point there. I don't think I'll go back into that one. But again, even as large as the sun is, we have vastly larger stars in our own galaxy. This is the photo I meant to show you last time. This is that photo that the Hubble Space Telescope took looking at the Big Dipper, Ursa Major, the Big Bear, also known as just an average area in the constellation, kind of in the middle of the bucket part. Nothing really was known there of any interest. So they just opened the big shutter on the front of the Space Telescope and just did an exposure for a full week. And of course, there's no problem with background glare of cities, obviously, because it's in space. And what we see are these weird-shaped galaxies, which seem to be in the process of forming probably at least around 11 billion years ago, roughly. So this is an example of what I was talking about, that if you can look at faint enough objects, you're generally looking at things that are farther away. So that's why we leave the flap open, because we want to accumulate light on our CCD. We're seeing dimmer things. Dimmer things are generally farther away. So this was actually, this is a famous photo called the Hubble Deep Field, which actually, by itself, kind of revolutionized cosmology, because what we actually saw were galaxies forming much earlier in the history of the universe than we actually expected to see them forming. In other words, galaxies are thought to take a long time to form because gas has to be pulled together slowly. But they were already forming these weird shapes, which probably coalesced to form normal galaxies, way back in this early epoch, which probably has something to do with the presence of black holes early on in the history of the universe. Oh, that's my cat. My cat. We have 5 cats. That's my special cat. Her name's Cheddar, because of the orange and white. And what was my point here? Yes, I guess I did have a point. Yeah. So in all this vastness that we're aware of, this universe that goes out for 13 billion light years, if you consider the complexity of the genetic code in any mammal, even a cat, there's actually, with the exception of actual twins, there's almost no chance of actually having duplicate structures like this anywhere else in the universe. So we believe that each of us truly are completely individual in our structure, because the complexity of the body is so high, the odds are essentially zero you can have duplication of that anyplace else, even for something like a cat. So even your pets are really completely unique in their own way. I think that's the reason I did this. That's the second floor of the kitty condo, by the way, poking out of it. All right, so I mentioned last time there's this historical connection with what we're going to be doing, because before there was astronomy, there was astrology, which we do not consider to be a science, of course. But astrology is sort of a social phenomenon, which we think has deep ties in the human psyche, because humans would look into the sky and they would see unchanging constellations and things like that, constellation patterns that don't change, and would try to connect themselves with this unchanging cosmic firmament, perhaps in order to gain some more meaning for their own lives. So whatever constellation was up the time that you were born was kind of your connection with the cosmic cycle, as it were. And was thought to be significant, because if that constellation was up when you were born, that's the kind of imprint of the universe at that moment. So it must have something to do with what happens later in your life. So now we look at this as a natural outcome of mankind's search for meaning and understanding of its place in the universe. But we don't see that as any kind of a scientific discipline anymore. There's absolutely no objective evidence that there's any validity to it. The scientific method took us from the Dark Ages with astrology and superstition into what we can now consider to be the modern scientific era. But it led to conflicts with religious dogmas that were very deeply ingrained at the time. Like, for example, the whole notion that the Earth is not at the center of the universe, right? Going back even a couple thousand years, it was believed that the Earth was at the center of everything. And that was also something that was ingrained in religious dogmas. So when somebody like Galileo here writes a popular book explaining that the sun is really at the center, the Earth is not at the center, it's actually the sun, this causes tremendous upheaval and actually leads to his personal persecution, and even him facing the Inquisition here, and then saying, look, sign this document here, buddy, or your history. Of course, it was history anyway, it was a historical figure. But they didn't know that at the time. And he actually did sign, but there's a famous quote that Of course, the point was he was supposed to renounce the idea that the Earth was going around the sun, because the religious dogma was that the sun's at the center, that the Earth's at the center, and the Earth doesn't move. That the sun has to be going around the Earth. So he signed a document that repudiated his view that the Earth actually did move. But as he walked away, he muttered under his breath, I can't remember the Latin, "Una cum laude," or something like that, which is actually the right quote. But it actually means, and yet it still moves. So, like, in other words, you can force me to sign this paper, but the Earth is still moving around the sun. I mean, we didn't change anything with that particular fact. So the scientific method leads us to try to understand an actual objective truth that everybody can measure and agree on. Just the idea of there being an objective truth that everybody can agree on based on measurements, that by itself actually was pretty revolutionary at the time. Okay, so the solar system, we're going to be basically spending our semester in here, and you'll be spending most of your lives probably in the solar system. What we see here is a pattern of planets that spreads out over ever-increasing distances from the sun. The closest planet to the sun is Mercury. Now, the scale that we're looking at here, with Pluto and Neptune visible, and this is drawn to the correct scale, so they didn't, we're not playing around with the scales, because the whole point of this is we want to see what the relative distances are. You can hardly see Mercury at the same scale where you wouldn't be able to view Neptune like this. So we have Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, Pluto. And Pluto, of course, isn't really a planet, but just for kind of, just out of sensitivity, it's still there in the panel itself. And we also have this feature between Mars and Jupiter, which is the asteroid belt, where we have a lot of asteroids hanging around. There's actually not a whole lot of matter in the asteroid belt, but it might have been able to form into another planet if it weren't for the perturbing influence of Jupiter. Jupiter is very massive and actually exerts a very strong gravitational field in the neighborhood, and probably would have destabilized any planet that was going to be able to form. Notice that the orbits are pretty much in the same plane. They're quite circular. Actually, all of these orbits are counterclockwise as viewed from above, from what we call the North Celestial Pole, which is way up high over Earth's North Pole. So we see patterns of regularity in the solar system already. We're going to be looking at the properties of the planets. We basically have two major categories. The inner planets have relatively high densities in grams per cubic centimeter here, compared to the outer planets, starting with Jupiter, have quite low densities that are actually approaching the density of liquid water. So we have the two categories of planets being the terrestrial or rocky planets, the more dense ones that are clustered close to the sun, and then the gas giant planets farther out. We're talking about that. Okay, so again, a sequence of planets. Now this again is completely not to scale. This is just an artist's conception so that we can get them all kind of, well, the sizes, I guess, are actually correct. The size of the sun compared to Jupiter is about right, though we just compressed them very, very close together. And what we see is a pretty motley crew of planets. I mean, there's not a lot of similarities between any two of these planets. So clearly they all went through different formation processes. We'd like to understand that because we ultimately want to understand how other solar systems can form. Now let me see if this is like that. Okay, pretty much the same sort of thing we were just talking about. The size scales are correct, but the distances are all wrong. Okay, so we look at the sky at night. We're able to see about 3,000 stars with the unaided eye. Probably no more than a few hundred in Fairfax because of the sky glow that we have due to our proximity to Washington. And of course we have constellations where we've culturally organized them into patterns that have some significance. So the patterns of constellations for Chinese people are different than what we use in the West here, for instance. These days, scientists use them to indicate general regions of the sky, kind of like states or provinces or something like that. And we have this concept of the celestial sphere. So we've already talked about diurnal motion. Diurnal motion is the apparent motion of the stars, which actually reflects the counterclockwise spin of the Earth, right? The stars are really motionless, and the Earth is just spinning counterclockwise, giving rise to the rising and setting phenomenon. But for convenience, we group all the stars together and call them the celestial sphere. And this celestial sphere seems to be spinning around us, rising in the east and setting in the west. So the celestial sphere is a set of all stars in the sky, basically. And we actually divide it into two hemispheres. There's a northern hemisphere and a southern hemisphere of the celestial sphere. There's actually an equator in the celestial sphere. We call it the celestial equator. The celestial equator is a projection of Earth's equator into space. The whole idea is that we want to be able to talk about the celestial sphere spinning around Earth. That's only going to happen if we actually, this axis, right up to the center, is the same as Earth's spin axis. So the point up there is what we call the north celestial pole. It's a projection of Earth's spin axis into space. That's the point around which we see those arcs when we look north. We see the counterclockwise motion around the north celestial pole when we look north. And there's actually a star pretty near the north celestial pole we call Polaris, the North Star, which is useful for navigation. There's actually a south celestial pole down here, which is a projection of Earth's spin axis in the opposite direction, but there just doesn't happen to be a star near the south celestial pole, so there's no southern Polaris, so to speak. You don't have that. Just by random coincidence, it does not happen to be a star near that point. And constellations sit on the celestial sphere, and the whole thing moves around. So the stars and the constellations move around on this sphere. So by itself, it wouldn't really be very useful if we didn't have a way to indicate a location of a star on this sphere.